Pressure-volume loops are the ultimate USMLE step 1 killer, and today I'm gonna show you one specific type of questions that 50% of test takers gets wrong. Let's see if you can solve it. So, patient has 3-day history of dyspnea, orthopnea and ankle edema. On the morning of the presentation she also developed nausea, vomiting and headache. Also she has significant elevation of blood pressure with pulmonary crackles. As a result, infusion of sodium nitroprusside was prescribed. And the question, which of the following left ventricular pressure-volume relationships best represents the effects of the therapy? Time's up. If you are struggling to find the answer, don't panic. Even the most complex step 1 questions are just variation of the basics. To make this clear, let's strip away the pathology for a moment and re-examine the... A volume pressure loop is essentially a map of one single cardiac cycle. It's built on two axes. The x-axis shows the volume of the blood inside the left ventricle, while the y-axis represents the pressure that the left ventricle generates. The loop is formed by 4 K changes, which mark the opening and closing of our valves. The lower points represent the mitral valve, and the higher points represent the aortic valve. Let's reveal the phases between these points, starting with the point 1. Point 1 is a moment of mitral valve closes, which generates the first heart sound. This is a critical landmark because it signals the beginning of the systole, or in other words, the absolute end of diastole. Because of this, the volume of blood at point 1 is known as end diastolic volume, or EDV. After the mitral valve closes, the left ventricle begins to contract. Pressure climbs rapidly, but since all valves are shut, the blood has nowhere to go. Because the volume stays exactly the same, this phase is called isovolumetric contraction. Iso means the same and volumetric means the volume. And here is a high yield step 1 tip. This is a period of heart highest oxygen consumption. At point 2, the pressure finally overcomes the aorta and the aortic valve open. Blood is pumped out, which is why we call this ejection phase. During this stage, the volume in the left ventricle drops until we reach the point 3, the moment of aortic valve closes. This closure isn't just a point of the graph, it's that produces the second heart sound and marks the official end of systole. The amount of blood remaining in the ventricle at this moment is your end systolic volume, or ESV. So, if we look at the entire top half of our loop from point 1 all the way to point 3, we are looking at the systole. After the aortic valve closes, diastole begins. The ventricles start to relax and pressure drops fast, but since all valves are still shut and blood has nowhere to go, volume stays the same, so we call it isovolumetric relaxation. It's exact opposite of what we saw earlier. The pressure keeps falling until we hit point 4, where the mitral valve opens and the ventricle starts to fill with blood very fast. This rapid flow is what creates the third heart sound. The filling continues more slowly until the very end, where the atrium gives one last squeeze, the atrial kick. This contraction produces the fourth heart sound right before mitral valve closes again at point 1. One more thing you need to know. The width of this loop represents your stroke volume. It's simply the difference between the blood you started with, or end diastolic volume, and the blood left over, or end systolic volume. To understand how the loop changes, we need to label 4 K drivers of the heart. First, preload. This is simply your end diastolic volume, the point where the heart is most full. The second, afterload. Think of this as the pressure the heart must fight against. It touches very peak of our graph. Third, contractility. This is the heart squeezing power, and it is represented by the slope that touches the point 3. And finally, compliance. This is how stretchy the ventricle is, and shown by the filling line at the bottom. Now let's see what happens when we mess with these variables. Starting with... When preload increases, it means we are starting with more blood, so our end-diastolic volume moves to the right. According to the Frank-Starling law, the more you stretch the heart, the harder it contracts. This means our stroke volume must increase, making the entire graph wider. More blood being pumped out also means a slight rise of afterload, so you will see a peak of the graph moves a little bit higher too. The result? A loop that stretches to the right and climbs slightly upward. Now let's look at decreased preload. This means we have less blood coming into the left ventricle, so our end-diastolic volume moves to the left. With less blood to pump, the stroke volume drops, and the entire graph becomes narrower. Because the heart isn't pushing out as much volume, the afterload also slightly decreases, meaning peak of the graph will sit just a little bit lower than before. In short, the loop shrinks from the right and drops slightly. Now let's talk about increased afterload. Remember, afterload is the pressure the heart has to fight against. If afterload goes up, the ventricle has to work much harder. This pushes point 2 and entire top curve higher. The heart is straining just to open the aortic valve. But because the resistance is so high, the ejection phase becomes shorter. The heart can't pump out as much blood, so point 3 slides up along the contractility line. This means more blood is left behind in the ventricle, so your end-systolic volume increases. The result? The graph gets taller, much narrower, meaning your stroke volume decreases. Now, what if afterload decreases? This means the pressure in the arteries is low and the heart doesn't have to fight as hard. Because there is less resistance, the ejection curve goes down and the whole loop becomes shorter. Our contractility stays the same, so the line doesn't move. Instead, the ejection curve simply slides down that line to a lower point. This means the heart empties itself much better. Your end-systolic volume drops and the graph stretches to the left, which means your stroke volume increases. Now let's talk about contractility. This is the heart's actual squeezing power. If the heart becomes stronger, the contractility line moves up and to the left. This pulls point 3 along with it. Because the heart is squeezing harder, it pumps out more blood and leaves less behind. This means your end-systolic volume drops and the graph becomes wider. Naturally, a wider graph means a higher stroke volume. And there is a quick reminder. Ejection fraction is just a ratio between the stroke volume and end-diastolic volume. So if your stroke volume goes up, your ejection fraction goes up too. But what happens when contractility decreases? The heart becomes weak and contractility line drops. You can imagine it like heavy lines that start to fall and push entire loop to the right. Look at the result. The heart can't pump effectively anymore, so blood stays inside and your end-systolic volume increases. Because the heart doesn't empty, it overfills, and end-diastolic volume increases too. The loop becomes shorter and much narrower. This means both your stroke volume and your ejection fraction are crashing. Now let's look at compliance. This is how stretchy the heart is. If the compliance decreases, the heart becomes stiff, like a balloon made of thick rubber. The compliance line at the bottom starts to rise. You can imagine the graph sliding down a hill in winter. As the line gets steeper, it pushes the entire loop down and to the left. The heart can't fill up properly anymore. Your end-diastolic volume drops significantly. Even if the heart is strong, it just doesn't have enough blood to work with. The result? The loop gets much smaller and shifts to the left, leading to a much lower stroke volume. Aortic stenosis is a great example of high afterload. This is when aortic valve is too narrow. Pay attention, the graph here looks exactly the same as our increased afterload loop. It is just as tall and just as narrow. If the stenosis is mild, your end diastolic volume stays the same. The heart just built up massive pressure to force blood through the tiny opening. But here is the high yield part. To survive this pressure, the heart muscle grows thicker, concentric hypertrophy. It becomes like a stiff, thick balloon. This decreases the compliance, and our graph starts to slide down that winter hill. This is how the pressure problem turns into diastolic heart failure. Now let's look at mitral stenosis. Here the problem is at the entrance. The inlet valve is narrow, so the ventricle can't fill up properly. Because of this, your end diastolic volume drops, and the graph shifts to the left. Our contractility hasn't changed, which means the heart can empty itself very effectively. Your end systolic volume drops too. The loop becomes narrower, so your stroke volume falls, and since less blood is being pumped out, your afterload slightly decreases as well. But where does all that blood go? It gets back up in the left atrium, where the pressure starts to climb dangerously high. Now look at the regurgitation graphs. They have a unique egg shape that you will never confuse with anything else. But how do you tell them apart? Let's start from aortic regurgitation. The main problem here is that the exit door doesn't close properly. At the point 3, the aortic valve should be shut, but it's leaking. As the pressure drops, blood starts flowing back into the ventricle from the aorta. This pushes point 4 to the right, significantly increasing your end diastolic volume. Even when the heart starts to squeeze, the pressure is still lower than in the aorta, so blood continues to leak in during the contraction. Because of this, there are no vertical lines, there are no true isovolumetric phases, because the volume is always changing. The loop becomes much wider, your stroke volume increases, and consequently your afterload rises slightly too. Now mitral regurgitation. Here the inlet valve is leaky. As soon as ventricle starts to squeeze at point 1, the pressure beats the left atrium, and the blood immediately starts to leaking back. The ventricle is losing volume from the very first millisecond. Because the blood has two ways out, the aorta and the atrium, the heart empties more completely. Your end systolic volume drops. Even after aortic valve closes, the pressure is still higher than the atrium, so the leak continues. Just like before, there are no vertical lines, no isovolumetric phases. When it's time to fill up again, all that leaked blood comes rushing back from the atrium, so your end diastolic volume increases. But don't be fooled. Even though the graph is wider and stroke volume looks huge, most of that blood is just swinging back and forth. The systemic stroke volume that actually reaches the body decreases, and your afterload slightly drops. Now let's come back to the case. First, we see dyspnea, orthopnea, and ankle edema. There are classic signs of heart failure when we have nausea, vomiting, and headache. This point directly to severe hypertension, the pulmonary crackles and pitting edema, and the diagnosis is clear. This is a heart failure caused by hypertensive emergency. Our drug of choice here is sodium nitroprusside. It works as powerful vasodilator for both veins and arteries. Arterial dilation leads to decrease in afterload. Venous dilation leads to decrease in preload. Now look at the graph changes. Decreasing in preload makes the graph narrower from the right side. Decreasing the afterload makes the graph shorter and allows it to widen back to the left. The result? The stroke volume remains the same, but the heart achieves it with much lower ventricular pressure. And that is how we find the correct answer. If you like the content and new format, please press like and subscribe buttons and have a good day.